All right, today is section 2.1, exponential functions and logistics functions. So here's a basic overview of some stuff. So logistics function, exponential functions. It's a function of this form right here, where you have a times some number to the power of x. This number right here would be the base number. That is the exponent. So the x is in the exponent. The number a is just some non-zero real number, and b is positive, and it can't be 1. So b is not going to be a negative in that sense. So that is what a basic exponential function is. In the big scheme of things, in word problem settings, a would be representing your initial value, the start value, and b is the base number. And if you remember from Algebra 1, this is related to a geometric series, and so the base number b would be considered the common ratio. So here's what you did. It's kind of hard to see. I'll zoom in here real quick. So here's a table 2 to the x. This is what you did in Algebra 1. And anytime I multiply to get to the next number in a table where these are going by ones, then that is an example of a geometric sequence, which we can then model using the base number would be 2, the repeated thing that you're multiplying by. And so then the base number b would be 2. The common ratio is 2. Okay. Now, we're going to go beyond and we're going to look at this number e. Base e is called the natural base. This e number is similar to what we have for the number pi. It is a symbol that represents a number that in decimal form, it goes on forever and ever and ever. It never stops. It never repeats. So the e value, just like pi, occurs very often in nature. So when we try and model nature and stuff, e is a lot of times being used. If I take this expression right here and I make the value n, just keep it getting bigger and bigger and bigger, then the bigger I make that, the closer the decimal I get for this comes to the letter e. So that's what this means. If n continues to infinity, keeps getting bigger forever, that's what that basically means, then this number gets closer and closer to e. Since we can't actually express e because it goes on forever and never stops and never repeats, this is the actual e number, and here is an approximation. So just like pi, this has an approximation. We usually use 2.718 to represent a decimal version of e. 2.718 is what we'll use for the number e in our calculator. Actually, our calculator will have the button e already, and you'll use that. But if you were doing it by hand, you can just use that because we round all our answers to 3 decimal places. So the base e. So exponential growth and decay functions. Let's take a look at the picture and how this is going to play out. Here's an exponential growth function. Here's a decay function. Here it is when the base number is not e. A is greater than 0, b is greater than 1. If b is greater than 1, then we have a growth function. Here, a is greater than 0, and b is between 0 and 1. So when the base number is between 0 and 1, whether in fraction form, between 0 and 1, or a decimal, doesn't matter, then you're going to get this decay look, as long as these conditions are met. Well, what if the base number is e? So they kind of like do this a lot. They'll talk about any base up here, and then when their e is the base number, it's a little bit different. Here's how they do this one. So just so you know, it means the same thing. So if the base number is e, then they put a letter up here, a value up here with the x. So here, notice there's a kx up here. process right here also works for any base. It doesn't just work for E, it works for all bases. This is just another way to look at growth functions. So these mean exactly the same thing. Okay? A is greater than 0 and K is greater than 0. So in other words, as long as the K value is a number bigger than 0, this would represent a growth function. But if K is negative, so if the exponent is negative, then I would get a decay. So let's stop and look at that for a second. Why? Give it to me this way. Why? Well, since it worked for any base, let's go back over to this thing. If I have this, and I'm telling you that the exponent is negative now, well, that negative exponent right here is just taking the base number and flipping it over. So when I tell you that E to a negative exponent, well, the negative exponent just flips E over to 1 over E, which is a fraction between 0 and 1. So that's why it's a decay. So they're just doing it a little bit differently, but it still means exactly the same thing. I can do the same thing if I have a B here. It doesn't have to be E. Remember, E is a specific number. I know it's kind of hard to remember that, but it is. It's a specific number. And B over here can be any base number. So if I do the same thing with a 3 here, if I have 3 to a kx and k is negative, then I get a decay function also. That's what I'm trying to get you to see. So what other conditions do we have with these two kind of graphs? All exponential graphs have a horizontal asymptote. What is a horizontal asymptote? It is a horizontal line that is not part of the graph, but it is a boundary of the graph. So it is a boundary line. It is a line that an exponential will not cross. That's what it is. We draw this into our graph picture as a dotted line because it is not part of the graph. If you graph it on your calculator, the calculator will not put it in at all. When you draw your hand drawings for me for exponential graphs, you will put it in as a dotted line. So if you look right here real closely, you'll see that we have a dotted line here. The parent function is at y equals 0. So the x-axis becomes the horizontal asymptote. And we just extend out in dotted line fashion and name it to indicate that that is my horizontal asymptote. So a horizontal asymptote is basically an end behavior asymptote. It tells me what happens at the ends of a graph. This particular graph has one end, this end, the right end, by the arrow indicates that it just keeps on going up and up and up forever, never, never. So there is no bound to that. There's nothing that's stopping it from going up. So there's no end behavior where the graph becomes something else on this side. But on this side over here, the farther out I go, the closer and closer that this end of the graph is going to look like the horizontal line, y equals 0. That's what it means. And just think about what happens, not up close, but don't even consider looking at anything before like a negative 1,000,000. What happens if I plug in x is a negative 1,000,000 in here? Well, I'm going to go out here, it's going to get really, 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 really small. It's going to become closer and closer to 0. That's what makes this an end behavior. That's why the horizontal line y equals 0 is a horizontal asymptote. On the decay side, this just flips over. And this over here becomes the end behavior on this side. As x goes to positive infinity, then this part of the graph gets closer and closer to 0. It never equals 0. It just gets closer to 0 the farther out you go. Again, we want to draw this dotted line. Now, why do these look like this? We also talked about transformations already. And in transformations, if I look at it from the point of view as this exponent is positive and this exponent is negative, so this is where the parenthesis is, and we can see that I have a negative with the x inside the parenthesis. And that indicates that we have a reflection across the y-axis. That's why these two are reflections of each other on the y-axis, because that's what's happening. Which brings us to the next part, the transformations. Here's your generic. I use E as the base number. I can use any base for this. It doesn't matter. The base number has nothing to do with the transformations whatsoever. Okay? So let me say that again. The base number has nothing to do with the transformations whatsoever. I don't care what the base number is. But just like when we talked about transformations before, we have stuff in the parentheses and stuff outside the parentheses. So I use the same letters as we did the last time we did transformations for memory purposes. The last time I showed it to you, we used the quadratic parent function. See, B, C, A, and D. And it serves the same, does the same thing for the exponential as it did for this. So if you guys remember that from before, plus D, up and down. A is your vertical stretches and shrinks. And if A is negative, then you have a reflection on the x-axis. And then the stuff B and C represent horizontal transformations. So part of what you're going to be asked to do is to identify transformations, and we'll do one of those examples at the end. How do I graph? I wrote it out for you. This is what I would do, and this is what I'm going to show you I'm going to do. You're going to make a table, usually 5 points. We want to take the exponent, all that stuff up here in the exponent. We're going to set it equal to 0. Find what makes it 0. That's going to be the middle of my table. I'm going to pick 2 numbers above that and 2 numbers below that. I'm going to graph those dots. I'm going to draw in the horizontal asymptote as a dotted line, and I'm going to name it. And once we have that, we can draw our picture, depending on how it is. If it's a growth, it'll look like this. A decay will look like this. If I have reflections, it could be upside down and all that kind of stuff, but we'll talk about that as we go. I'm going to do one of those for you right now. I'll do a freehand drawing. Let's take a look at this one right here. So I want to graph this. I'll also look at how to describe the transformation. Since this up here is the parenthesis part, I can see clearly that I'm going to move it up 1 unit. What do I do for the transformations? I take that quantity right there, set it equal to 0. The solution to this tells me if I need to move right or left. So based off of this, so positive 2 means I'm going to go to the right 2 units. And then I have a negative in front of the x, so that is a reflection across the y-axis. And then I have to go up 1 unit. So that's how I would list the transformations from that. In the graphing sense, I want to make my table. And that number serves 2 purposes. Not only does it tell me right or left, it also tells me in the middle of my table, I'm going to center this graph around the number 2. I'm going to pick 2 numbers above it, 2 numbers below it. I might need another one. Just be aware, I might need another one just to make sure that it points in the right direction. Okay. And we'll talk about that if we deal with that. So now what? We'll just plug numbers in. If I take the 2 and plug it in, I got an exponent that's 0. 4 to the 0 power is 1. 1 plus 1 is 2. If I plug in 3 up here, I'll get 2 minus 3, which is negative 1. So if you need it, 4 to the negative 1 plus 1, that is going to be a fraction, 1/4. So I get 1 and 1/4, and you can just write 1 and 1/4. You don't need to. This is the one time you can use a mixed number because it's quicker. Okay? If I plug in 4, then I'm going to get 4 to the negative 2 plus 1. This is going to be 1 over 4 squared, and that's 1 over 16. So this is going to be 1 and 1/16. And so you can see the farther out I go, the smaller this is going to get, or the closer it's going to get to the number 1. And we'll talk about that here in a minute. So what you are learning here is for exponential graphs, the horizontal asymptote is going to be whatever D is. Your up or down tells you where the horizontal asymptote is at. Your up or down tells you where your horizontal asymptote is at. You might want to write that down. Your up and down number tells you where the horizontal asymptote is going to be. And like so continuing our table, we can plug in a 1. Then I get 2 minus 1 is 1, so 4 to the 1 is 4. And so that'll be a 5. If I plug in 0, I'll get 4 squared, which is 16 plus 1, 17. And so then we can now draw our picture. Make sure your graphs are on graph paper. Because there's no negative values, I don't need a large negative realm. I got to go all the way out to 4. And you can go one more than that. And we got to go up to 17. And I'm not going to make it. That's fine. -1, -1, 1, 2, 3, 4, 5, 5, 6, 7, 8. So we have a dotted line at 1. I always draw my horizontal asymptote in first. Arrows on each end. Y equals 1. You name it. Then put your dots in. 1 goes to 5. 2 goes to 2. And then these are getting closer and closer to 1, obviously. And then at 0, I'm supposed to be at 17. Well, I'm not going to make it to 17. But if that's 8, then 17 is going to be somewhere up here. So when I draw this, I want to aim for that dot. Don't cross the y-axis because you're not crossing the y-axis until you get up here at 17. So when you draw it, I usually tell people to draw it kind of like you're going to plant your heel of your hand, and you want to be able to run along this line and then touch all those points. So as long as you can do that, you're pretty good to go. Draw it out. Stay right on top of the line like that. And once you get to the dots, start curving it up. And then it gets really, really steep, really, really fast. And then aim for that dot up there. Exponential. Okay? You want to name some points. I want you to name at least 2 points. 1 point must be the center point. Your new center point must be labeled. So that's the one I must be labeled. And then just pick the next easiest one. Usually that one right there is probably the easiest one from there. And that graph is what I'm looking for. So that's how you go through the graphing process. Part of what you're going to be doing in your homework is going to be graphing these things out, identifying the horizontal asymptote and the transformations. Now, the second function that you're going to look at is called the logistics function, but let's talk about this part first. In the real world, some things are limited on how much they can grow. For example, how tall a tree gets or how many fish can survive in a lake. To more accurately represent these types of situations, we will use what's called a logistics growth function. All right, I'm going to move on. So what is the logistics growth function? They look like this. A, B, C, K are positive constants. B is less than 1. So if B is less than 1, then B is like a fraction. That's why you see E has a negative exponent here. So it can be written in either one of these 2 forms. If it's written in this form, remember that B has to be a fraction between 0 and 1. And E is just a number, but the exponent is negative, indicating that E is 1 over E. Okay? Because it's a fraction. So in this situation, the number C is the limit to growth. Okay? A logistics growth function will have two horizontal asymptotes. Unless you have movements in some fashion, one is going to be at 0 and the other one is going to be at C. This is an example of the parent function for logistics. So the C is a 1. You can see that K is 1, A is 1, your parent function right here. So you'll notice that you have a horizontal asymptote at 0, and then another one at 1. As you do word problems on this, and we'll talk more about those in the next time, for short-term time spans, so for short time spans, a lot of times they'll use the exponential growth function, the previous one, the growth or decay. Okay, they'll use that one for short term, for short timers, to represent population growths. But for longer time spans, this is a much better model. So what you're going to be asked to do on this in this lesson mostly is identify transformations and to graph these functions out. So I graphed one for you already. We're going to go ahead and take a look at some of the other questions we might have outside the video.